This is GAD210, Tech Art and Game Engine Scripting, and we're going to take a little bit of a look at how computers work. So sometimes computers can be a bit of a black box, and even though we use them quite a lot, we don't really know maybe what goes on inside them. We know that we plug them into electricity. We know that inside somewhere is some kind of processor. There's maybe some RAM or some memory, and there's some kind of hard drives and stuff, and then we plug in keyboards and monitors. But how does then that hardware get put to work to actually do what we want? So the basic computer architecture from a kind of a bird's eye view is that there's some sort of processor right here. This guy here is what we would call like the computer chip, right? And that has a set of instructions that are essentially burned onto it, right? That are created by Intel or by AMD or by whatever the chip manufacturer is. And it's not just personal computers. It could be for calculators. It could be for logic controllers in, say, an elevator. Any kind of computer chip has some kind of addressable instructions, so commands that you can give it in order for it to change the way that electricity flows through it, to change the pathways between the little metal legs that you see that you get kind of soldered onto the whatever circuit boards you have. So it's a bit like a massive switchboard that you can kind of configure, right? And on the computer is a little bit of storage space. These are the registers, okay? And that's a small amount of extremely fast storage space that sits on a computer chip, a processor. And it's good to have it right there because it's very quick for the computer to access that data. So if your program is using data frequently, it will end up in the registers, and then the CPU will be able to access it very, very quickly. Often also a computer might have an arithmetic logic unit. So this is responsible for doing, say, floating point calculations, so decimal point numbers as opposed to integers. But the CPU will have, like I said, at the factory kind of burned into it, it will know how to do things like add integers together and take them away from each other and perform floating point calculations as well. And it will know how to retrieve data from memory and to write it back to the memory as well. So all of those things kind of come built in. How advanced they are and how fast it is all just depends on the chip and the manufacturer. So that's the basic function of that. In order for it to do pretty much anything useful, right, if it wants to request some data and that data doesn't already exist in the registers, it will go and ask for that data, and it will go out onto this thing here is like the bus. This kind of whole big L-shaped thing here is the bus. And you can think of it kind of like a sushi train, right? So information kind of is like a sushi train, and it just kind of, if you want to put a request to ask for something, you put it onto the bus, and that request comes down here, and it comes into the main memory and says, do you have the information that I want? And then main memory says yes or no. And if it does, so that's your RAM on your computer, and if it does, it'll put the answer back onto the sushi train, and that will kind of come back to the processor, right? So how fast that happens is really important for how fast a computer can run. So the sushi train, right, the bus has its own kind of frequency that runs at. So you might have heard of the bus speed of your motherboard, something like that. That will determine how quickly messages and data can flow between memory and your processor. Notice that the registers don't use the bus, and they're really, really fast. So ultimately, you want to have your data in the registers, but there's only a small amount of them, as in really small. A very, very small amount can go in the registers. You'll have secondary caches and that kind of thing. So L1 cache and L2 cache are kind of extensions of this. They're not represented in this diagram. But the next fastest thing you have is main memory, and that's probably it's a couple of 100 times slower, really, than getting something from the registers. So going out to main memory, to RAM, is slower than registers. But even worse is, if it's not in main memory, then we have to get it off secondary storage, and that would be something like your hard drive or your SSD. So all of that is kind of counted as secondary storage. And that's, again, hundreds of times slower than getting it from main memory. So this is kind of the equivalent, I guess, would be if I was the CPU and I wanted something and it was on the registers, it'd be like reaching into my pocket. If I wanted to get it from main memory, it would mean maybe I have to walk out of the current room I'm in and into the next room to get it. And if I need to get it from secondary storage, maybe I need to go out of this building and into the next house, or the next building, and get it from there and bring it back. Okay, so that's kind of how slow these things are. If then you had to go get it from something like a USB stick, is even slower again. Maybe that would be like a couple of buildings across. And if you have to go get it from the internet, like from the network, again, that can be even slower. More like needing to walk to the next suburb, something like that. So these things, this information kind of flows into the CPU, and it can make decisions based on the information and based on the program that it's been fed. So the program comes generally, it's on your hard drive, it gets loaded into the main memory here, and then gets put into the CPU kind of line by line or instruction by instruction, and the CPU kind of runs it, and it updates the value of its registers with every instruction. And that's kind of like its little notepad of what it's tracking. So that's the kind of basic part of how computers work. And then we have things like keyboard and mouse kind of contribute to messages that get put on that bus as well. And then the kind of input devices. And then we can also display out to a monitor or print something out to a printer. So all of that uses this kind of bus in here. And generally you want the bus to be somewhat compatible with the speeds of your memory to make best use of it. So there's some kind of parity or multiplication, clean multiple of the speed of your memory and the speed of your bus. And that will optimize kind of how quick your computer can process instructions. So that's a basic kind of breakdown of it. So a massive big program like the operating system that sits on your computer that manages all your hardware, like Windows or Linux or Mac OS, is really just a great big program that sits in your on a hard drive and gets read into memory, and then it essentially manipulates the CPU into doing what you want, like running more programs or games or whatever it is. So that's kind of computer at a bird's eye view. At a really detailed view, we have the CPU here, which, like I said, has a whole bunch of kind of pre-built instructions already put into it that it knows how to run, I guess. And it can execute billions of these per second. When you write a program and it gets kind of turned into something that the computer, so no matter what language it's in, ultimately the only thing that the computer can really run is being told, I want you to run this instruction that's built into you, and here's some data that you can use to run that instruction. So this is what it looks like. These values here are increasing memory addresses in RAM, okay, that contain program code. Each one of these is another memory address, and this is the actual code that's stored at that address, okay, this kind of section here. And that's what the computer sees. This entire column is what the computer executes, and to us it just looks like kind of nothing. So we need a way to kind of translate that between something that humans can write and something that the computer can write. So the first way that we really had of doing that, rather than actually specifying these values directly to the computer, which is what the earliest kind of programmers did, they invented a language called assembly. And assembly looked like this part here, these columns. And what this is the first number here is code for the jump instruction. And then the rest of the instruction, jumps, is an instruction that changes the current execution point to a new memory address, and that memory address is here. It's specified that it should take 2 bytes. So there you go. This bit of code written by a programmer, jump to this location, was translated into this bit of code for the CPU, which executes instruction 6C, which is the CPU's jump instruction, and with this data. Now you'll notice it's backwards, right? 36 comes before the 00, whereas where it was said by the programmer it was the other way around. This is just a byte ordering thing. Don't worry too much about it. But essentially, this is a translation between, I guess, human code and computer code. Again, so then we have a compare instruction here. I want you to compare whatever is in a certain register to this value here. And here we have it. C9 is the compare instruction. So if we have another compare down here, let me see. We do. We've got another compare here. I bet it's C9. There it is. It's C9. So there's a clear kind of translation between whatever you write as a human and what the computer has to write. There's a whole bunch of different ones here. This is a jump instruction based on whether there's a certain result in a certain register. This is an AND, a binary AND instruction. This looks like a decrement and check if something's equal. A branch if equal. Okay, so branch to a certain address if the value in a register was equal to something. So that's essentially what's happening. Okay, the good news is you don't have to write machine code because that would be very hard, and you also don't have to write assembly code because that would also be very hard. And the assembly code matters. It matters which type of CPU you're executing it on. The assembly code on an AMD chip may be slightly different to an Intel chip, and that would be very different to, say, you can write assembly code for Texas Instrument calculator chips or chips in other types of computers like a PlayStation or whatnot. So the assembly code and the compiled machine code that it gets translated into, they vary from machine to machine. Ultimately, though, this assembly code would have been written in a text file, and then a program would have turned it into the machine code. So this would have been a very old way of programming, but you're essentially thinking about it as you are manipulating the CPU into doing what you want. In general, okay, we have these programming languages. Assembly was one of them, but in general, we have all sorts of programming languages, and they all do the same basic thing, which is we allowing humans to give instructions to computers. And ultimately, the computer can only run it in its own kind of native code, its own native machine language. But luckily, the people that make the programming languages handle the translation for us. So you would have heard of languages like Python or Ruby or C or Java or C++ or Pascal or Clojure, C# and JavaScript. They're all examples of different types of programming languages. They have similar concepts, but pretty much the way you would write them is different for all of them. Okay, and all of it is just text in a text file. So you don't need anything special. You just need a text editor. And the computer then will read that text file, and there'll be a program on the computer that reads and makes sure that the text file, the code or the words, obey the syntax of the language that you're writing, the rules of the language. And if they do, it will then turn it into something that the computer can run. So it generally will turn it into another format once it's been processed so that it can be executed quickly. So it doesn't have to kind of read it line by line every time. If it reads it once and says, yep, this is right, it'll transform it into machine code or something. So this is the general idea. You code in, say, C# or C++ or C or whatever language it is. Something, a part of that language's kind of installed kind of program can turn that into, can read that file and turn it into something that can run on the computer, and then that gets executed. Okay? So you write it, you code it in a text file. There's something that takes your text file and interprets it or compiles it into machine code, and then we execute that. We tell the computer, run the machine code. The computer can't run the code. Something has to do the middle step. Okay. In this unit, we'll be using C#, and that will use there'll be some kind of C# interpreter compiler that will do that work for you. So what do we mean when we say compile? Well, compile is what we would do with the very first languages that we had. We had to compile those into machine code, and that's the instructions for the CPU. So assembly, like you saw earlier, but also languages like C and Fortran, and later C++. So these all, once you write your code, right? Here, this is an example of say some, let me see, it looks like C code. The compiler needs to turn that into what you saw before, the machine code. Okay? And, oops, I'll get rid of that. And so you write your code, you run the compiler says, did it obey all the rules? Did you make any typos, or did you spell anything wrong? And if you didn't, it would spit out something that you can run. And that can still have errors. It could still have a problem in it. If it did, and you ran it, and it had a problem, it would just crash. So it would either hang or the program would kind of end, right? And that could potentially crash the whole computer. So definitely history is littered with programmers that have crashed entire kind of systems. Interpreted languages came a bit later, and it's a similar concept, except if you think about the compiled languages, they need to produce assembler or machine code that runs on a particular CPU. So if you then switched to a different type of system, a different type of hardware system with a different CPU, you would maybe have to change the code you wrote at least a bit. Okay, and that kind of sucks. So if you're switching between Linux and Windows, or you're switching between Intel and you're switching between Intel and AMD or something like that, you may have to change your code, or at least change your compiler. In an interpreted language, or languages that came along later, what they did was they said, instead of having to change your code every time you want to be on a new system, we'll make an environment, right, a program that your code runs inside, and that's called the runtime environment. And we'll make one for Linux, and one for Windows, and one for Mac. And we'll make it for Windows with a 32-bit system, or Windows with a 64-bit system. We'll make it for Linux with a 32-bit system, or Linux with a 64-bit system. So they would make it for every combination of hardware and software that you could get. And then your code doesn't need to care. It can just run for whatever environment it's in. Okay, so you may have heard of Java. That has the JRE. You write Java code, it runs in the JRE, and Sun, which is the company that makes Java, makes sure that there's a JRE for every operating system and hardware combination out there. JavaScript is code that runs inside a web browser like Chrome or Firefox. So it doesn't matter. Your JavaScript doesn't change between the different browsers. The browser takes care of kind of running your code for you. Python comes with its own environment as well, and we will be using C#, which runs inside the Mono environment. Okay, so you kind of, for something like Java, you write your code for the JRE. You don't have to worry what operating system you're on or what hardware you're on. The JRE handles that for you. So all of the generation of the kind of machine code and all that kind of stuff is handled for you. So code doesn't have to really change between platforms, but it's the same thing. You write the code, something interprets the code, and it tells you any errors, if there are any, that it can see. And the worst that can happen, though, if you run the code and it doesn't work, is it might crash the runtime environment, but it won't crash the operating system, or it shouldn't. So it kind of protects you from crashing the whole system. So at first, these languages you would make them, even Java was like this, and it would be interpreted by the runtime environment, and it would often have a virtual machine built into it. It would be interpreted line by line, right? And that's very slow to do. So eventually they worked out a way where you could essentially compile a language like Java for the JRE, so it would run a lot faster. And this is the case with something like C# as well. So in this unit, we'll learn C#, since that works with Unity. It's a strongly typed language, so you have to declare your variables before you use them and say what type they are. And it supports object-oriented programming, meaning we can model the kind of objects and interactions as classes, and we learn about that during the unit. And it runs on the mono runtime environment. So that's the .NET environment you might have heard of, which means it's compiled, but it's not compiled like C or C++ is compiled for the hardware. It's compiled for the environment. So we are somewhat protected from totally crashing the computer that we're on.